1903, the French chemist Edward Benedictus invented the world's first piece of safety glass by accident when he dropped a beaker which was coated with a plastic cellulose nitrate. The beaker cracked but didn't shatter. In 1939, it was used in World War II as armor for vehicles and soldiers. The typical structure of bulletproof glass includes multiple layers of glass and polycarbonate, which help to absorb the energy of impact. Fast forward to 2015, and we have made leaps and bounds in bulletproof glass technology. Not only are we able to stop more bullets, but those of higher caliber as well. Polymeric materials have shown great promise in transparent armor applications. The advantage of polymeric materials over their ceramic counterparts comes from their superior strength to weight ratio. While commercially available products have proven to be effective, they have yet to achieve a high enough strength at a practical thickness to be a viable replacement to the current ceramic technologies. Our idea is to incorporate graphene, known for its incredible strength at atomic thicknesses, onto a high-strength polymeric substrate. It is our hope that a laminated composite of graphene and polyurethane will be strong enough to stop ballistic impact at a reasonable thickness.
For this project, we chose to work with polyurethanes since it has some of the best impact resistance of any class of polymer. This is why it's commonly seen in car bumpers and protective equipment for team sports. Polyurethane also has the advantage of being able to be optically clear, which is not possible for ultra-high molecular weight polyethylene or other high-strength polymers.
We chose graphene because it's the strongest material known to man when it's in its pristine state. For this reason, we thought it would be a good material to use to enhance the mechanical properties of the polyurethane.
For this project, we chose a combination of VESTA, VASP, and Deep Thought because they not only allowed us to create 3D models of our system, but solve for the spring constant and elastic modulus.
Using visualization for electronic and structural analysis, or VESTA, we were able to create 3D models of our graphene and polyurethane. Working closely with John Meacham, we were able to take our 3D models and perform energy minimization, spring constant, and elastic modulus calculations via UMD's Deep Thought supercomputer.
For ballistic modeling, we used ANSYS Workbench for contact mechanics and impact. We use this program because it can model both nanometer and millimeter scale objects. This is ideal for a graphene and polyurethane composite.
We started ballistic modeling by performing Hertzian mechanics simulations to ensure analysis systems, or ANSYS, was producing valid results. We then moved on to more complicated regimes that matched our layered composite system.
Although we initially wanted to purchase graphene, we found it was more cost-effective to produce it in-house. So we decided to grow it via CVD, or chemical vapor deposition.
To fabricate our sheets of graphene onto copper foil, we started by purging the chamber with a mixture of hydrogen, methane, and argon. Next, we raised the temperature of the tube furnace to 1,000 degrees Celsius, which created an ideal environment for monolayer graphene growth. For the polymeric layer of our composite, we used a commercially available 2-part polyurethane resin. This particular formula was easy to work with and remained optically clear even after curing.
To create a robust and repeatable fabrication procedure, we used a layer-by-layer manufacturing process. We first started with our graphene and built our composite up from there.
Using chemical vapor deposition, graphene is grown onto copper foil. A polymeric support layer is then spin-coated on top of the module. This support layer is allowed to cure in preparation for the etching process. Using APS 100 as the copper etchant, the underlying graphene layer and copper foil are removed. Using polyurethane as the adhesive layer, the remaining modules are stacked together to create a laminated composite. Our models have shown a considerable reduction in kinetic energy and velocity compared to regular polyurethane. We were able to develop a cost-efficient method for bench scale fabrication of our layered composite. Finally, we were able to show that our polyurethane and graphene composite is a promising material for transparent armor.